For now, we have Shiyu, who's going to be giving the hands-on 2 session. Another reminder, feel free to ask questions if you're on Zoom in the chat, or if you're in the audience today, just raise your hand and ask questions as we're going along. You don't have to wait till the end or anything. Another reminder that the instructions that Shiyu is going to be discussing today are on the GitHub repo. Shiyu, maybe you can show them exactly what folder it is in.
Okay.
The link to this GitHub repo was sent in the original email from like 2 days ago. So yeah, it's in Perturbo Workshop 2023 and then hands-on 2, that folder. So you can follow along on this reading. All right, thanks. You can start, Shiyu.
Okay, thank you. Hi, everyone. Welcome to the hands-on session 2. I'm Shiyu and just joined the Professor Baladi's group this July. So in hands-on session 2, I will show you how to generate the EPR file step by step, which is the most important file for the following Perturbo calculations. Actually, you have the EPR file, you have everything with Perturbo, yeah. So you can feel free to stop me and raise a question whenever you want. So the hands-on session is totally interactive. We don't care about the smooth, but care about whether you can follow us and what's the question and whether you can reproduce the expected results. So let's start. Okay, I guess most of you have created follow the steps by Sergey in hands-on session 1, and I guess you have created the Docker container. It's the essential component for our following calculations. But if you don't create it just now, but would like to follow us this time, so it's a chance from here. You can just copy the command here. I will quickly review it. Okay, from the home folder and start from here. You can make a work folder to avoid affecting your other folders in this main folder, and then git clone this workshop repo. And then we need to approve the Docker image and then create the container. So any questions for the Docker container? So if it's okay, I will start. Okay, I will create the container. Now we are in the Docker. Just to make sure you can install the Perturbo-code, because we need to use it for the post-processing for the band, phonon, dispersion interpolation. And also for the Perturbo calculation, we suggest the folder hierarchy here, the PWPH1 for the preliminary steps, and then the QE2per for the interface between the external codes and Perturbo. The next one is the Perturbo. Okay, so if you have succeed in downloading the workshop material, you can see in the Docker, you can see the folder is here and go into here. Now we are the hands-on session 2. So go into the hands-on session 2 folder. Yes, and then in the tutorial by Yao, he showed the example of silicon. Here we show a different example of gallium arsenide. Okay, we start from the go into the PWPH folder and then go to the SF folder. We start from here. For the preliminary steps, the converged charge density is the basis of everything. So we need to run the SF calculation. Before that, if your computer has multiple cores, we strongly recommend you to set this parameter for the OpenMP number thrice, which will make your calculation fast. for me, I set it equals 6. Okay. Before that, I would like to show you once again of the input file. This is a very standard input file for a SF calculation with quantum expression. The most important parameters is the calculation type. Here is the SCF, and the other one is the lattice structure, which is the material you want to calculate. Okay, so just run it. You can see the output on the screen. Because we adopt a very cross-grade mesh, so it's very fast. When you see the job done, it means your calculation is successful. Any question here? Okay, so let's move on. After the SF calculation, we need to go to the phonon folder to do the phonon calculation, which is based on the SF converged charge density, because the DFPT is a perturbation theory for the electronic wave function. Here, we need to copy the charge density from the SF calculation into this folder, right? And then we copy the phonon.x to execute this calculation. Yeah. The phonon calculation is also adopt a 2x2x2 Q point grid but even though this we need to take more than 10 minutes, so it's so we will not to run it here just to show you. So please press the Ctrl+C to stop this running, and we have prepared a file for you. After this, we need to execute. Actually, we need to execute the script in the markdown file to connect the phonon information from the temp folder into another folder named save, which will be used for the following QE2per.
Question. Here you copy the temp file into the current folder. Why can't you link it? I just try to link it.
But I don't recommend, because maybe he will write something into this folder.
But the link should be able to make it directly to the file.
I mean, the SF template will be used for the NSF later. So if you have read something into this folder, maybe it will be changed. Yeah. So you can, any other question? Yeah, for that question, I mean, for other calculation, if the subroutine just read the information in the temp folder, it's very safe to make the softening. But if you don't make sure, for example, if the subroutine will write something into the folder, yeah, it will be erased, the original data. So then we execute this script to collect the information for the following calculation. And because we didn't finish the calculation for phonon, so there are some errors, but I just show you the step. So next, please to delete these two files. Okay. And then copy the file I prepared for you in the reference folder here. And then you can see there is a folder named save, which is the information for the QE2per. So any question, any problem? From the phonon calculation, even we take a 2x2x2, it takes more than 10 minutes, which means the phone calculation is really is a computational very expensive. And then please go to the non-SF calculation.
Just a very small question. So the values for all the input files, those are already converged values, or for those problems, or
Yeah.
if you really want to do Gaussian Masonite, those are the values you would use.
Yeah.
Okay.
For
So those are not tests.
could you repeat?
So
I mean,
yeah, no, that for like actual calculations, if like I'm doing slightly higher grades.
Okay.
These are just so that.
Okay, and the grid takes a lot of time, so
yeah. Just
the cutoff and everything is
just an minimal working example. Yeah.
Right. Yes.
If you want some, for example, the transport calculation, maybe the Q grid and the K grid should be very dense, but for interpolation, it's enough. Yeah.
Where do you get the references? Where are the references?
In the phone folder, there is no for you. Do you download the workshop material today?
Not today, but 2 days
Yeah,
ago.
we updated it yesterday.
Okay.
So I will wait here for you, so you can
Oh,
download
okay.
it now. Yeah. You can change another folder to download and then copy it to the, yeah. Yeah, before that, I forgot to mention, before the tutorial, there is a picture which mentioned by Yao. So because the whole calculation is very long, to make sure you are not lost in the workflow, so please, we strongly recommend you keep this picture in mind, and then you will know where you are during the workflows. When you finish, please tell me.
Well, you
Oh,
can
okay.
have
Okay.
I'm able to follow.
So then we need to go to the non-SF calculation. Here, you can look into the input file. The difference with the SF calculation is the first parameter is the calculation type should be non-SF. Then it will read the charge density from the temp folder and will not converge it once again. It can save your time. Another is the key mesh. The key mesh is what you want to perform the calculation for the key point in the list one by one. Because we need to do the interpolation using the volume 90 software. So here we will not use the reduced brain room. We should perform the calculation for the whole brain room. Maybe you want to adopt a different key mesh. Under this case, you can run a script, means key mesh, then pl, which is included in the volume 90 software. But because it's not included in the Docker, so we will not show it here. Okay, so let's run it. First, we need to copy the converged charge density from the SF calculation here. Okay, and then copy the command and to execute it. We can say it just needs to do some diagonalization because the charge density is converged. Any questions here? So I guess you can ask any question because there are many senior group members here. They can ask the question from you. Okay, so the job is done. Now we can show you the temp folder, where is in the temp folder, and then the Garnier arsenide save folder. There are many wave function and a charge density HDF5 file. You can see we adopt 4x4x4. So in total, the number of key point is 64. So for the 1 year function, there are 64 HDF5 files. Then let's move to the 1 year revision step. Go to the 1 folder. First, we need to make a temp folder and go into a temp folder. Because the 1 year 90 subroutine just read the information from the non-SCF folder. So you can just make a soft name. Okay. And then go out to the 1 folder. First, we need to generate the nearest neighbor for the key point in key space. So we need to an additional step. After that, you can find there is a NNKP file. And then we need to produce some overlap matrix and the agent values from the DFT for the 1 year 90, which is an external interface from the quantum expression. You can just run it. Now is the AMN. AMN means project the agent functions to the local orbitals, the projector you assigned in the 1 year.in file. And then is the MMN. Okay, so after that, you can see there are very important 3 files is AMN, MMN, and EIG. After that, you can do the linearization. Before that, I would like to show you the input file of the 1 year 90. The most important is first is the projectors based on your physics intuition and answers based on what orbitals you want to interpolate. It's actually your basis of the 1 year Hamiltonian in the real space. And then is the key point group grid, which should be consistent with the non-SCF calculation. And then we need to net the 1 year 90 subroutine to output the unitary matrix and the 1 year center. So these 2 parameters should be changed to true. And then let's execute. It's very fast. You can see there are this file, the U match and the U disentanglement match. For some case, if the number of band equals the number of 1 year, maybe there will not the disentanglement step. So in that case, there will not be the U dis match, but it's okay for the QE to perform the calculation. After that, we have all the files for the QE to per. So let's move on. Before that, any question? Okay, so let's move on to the QE to per folder.
So sorry, maybe I didn't quite get it. In this procedure, this gallium arsenide dot win.
Yeah.
I mean, is there a line missing to go back, or should I copy it in a temporary file, or I didn't catch it.
You mean copy the, yeah, you mean the temp folder here? Yeah, because
no, this just one step before. Can you go one step before?
you mean for a phonon or NSF?
No, the one after this ML, this one.
This
right?
one, right? Oh, okay. This
Okay,
one?
so yeah, you load this, and then it tells me that there is this gallium arsenide.win is missing, but this is in a folder over that. So
Yeah,
should we copy that, or?
it's over there, just over there. You don't need to copy. It's in the folder here. It's already in the folder before our calculation. It's the
Yeah, so I go out of the temporary folder again. Or, yeah,
Go out of.
I will figure it out. Maybe it's coming. Yeah, thanks.
Okay. Yeah, the workflows is very complex, and sometimes we mixed. Yeah, so. And then when we continue the QE to PERT calculation, which is most important because it will based on will produce the EPR file based on the DFT calculations and DFPD calculations and the linearization step. So it needs a huge number of files. So first is the non-SF calculation. Let's make a temp folder, go into the temp folder and to make a softening. Okay. And go out to make several softening for the 3 files in the linearization step. All you need to do is just to copy and to paste. If for your case, the number of bands equals the number of linear orbitals, so there will not be this file in the linearization step. So you can skip this step here and move on to the next step. Okay. And before that, we can look into the QE to PERT input file. It's very, very simple. Maybe you are aware that we don't copy the phonon the results here because we indicated the part here. And this is the key point grid. And this is the DFT band because we need to, the electron phonon coupling has the band index. So you should assign a band window. Okay, so let's execute the QE to PERT.x. Guess it's very quick. Okay, it finished. So now you can see we have the EPR file with a prefix. Actually, it's HDF5 format, so we cannot use the text editor to say it. Okay, now we have finished the task 1 because we have already generated the EPR file, which is the essential material for the following perturbo calculation. So any questions here? Wow, good job. Okay, so yeah, because if you just need to do some very standard calculation, for example, the functionalities have already been released in the Perturbo. You just need to treat the EPR file as a black box. You don't need to know what's in the EPR file. But I know there are many senior developers in among you, so maybe you need to do some specific post-processing based on the EPR file. So in the task 2, I would like to show you how to get access the EPR file. There are some tools. The first one is the HDF5 view. It should be installed in your local computer OS. I mean, not in a Docker. So if you don't want to install it, you can just watch me. I will show you how to use it. Okay, so let's go to the local OS.
Can you make the window on the right smaller?
Okay.
We cannot, I mean, we cannot see the last line you are typing.
Oh, okay. Thank you. Well, can you hear? It's good now? Okay. Go to the QE tuber. Open it. So we know. And then we need to open HDF5 view. You can see there are, except for the menu bar, there are 2 panels. What you need to do is just to drag the EPR file to the left panel and then drop. Okay. So you can see there are some information here. For HDF5 file, there are 2 data structure. One is the group, something like the folders. And the other one is the data set, something like the NumPy arrays. Okay. So we can just connect and see. This is the top level. The general information tells us there are 3 groups, which means the 4 groups. The 4 data are something like the folder. We can connect them one by one. For the basic data, you can see there are some basic information here. This is the lattice constant. This is whether you want to perform a polar calculation or not. This is the mass, number of atoms, number of symmetry operators. Okay. Linear centers. For the second one is the linear electron linear Hamiltonian. It's actually the Hamiltonian in the real space by interpolated with the variant software. The third one is the electron phonon matrix. Based on the linear functions you got from the linearization step. The last one is the force constant. Okay. So this is the first approach, and then let's move back to our Docker. Wow. The second method is just to use the command line command h5 ls. Okay, you can see there are 4 groups. You can go further, see the basic data. You can see there are several data sets, but you can't go into the data set inner. I mean, you can't show the elements here. For example, it just tells us it's a data set of HDF5 file. So the last approach is use the Python library H5Py. I have prepared a script here. First, we need to install the H5Py libraries and to import it, because if you want to show it the content in the data set, you need to convert the data type into NumPy array. So we need to import NumPy, and then to read the file, and then to show the file. Now I will show you what you just need to do is to run it, use the Python 3 access. Okay, so there are many data.
I just adjust the window because it's unavoidable.
Uh-huh.
So we cannot see the next.
The last line, right?
It's not.
Yeah.
Okay. Yeah, so thank you for letting me know this. And then let's pass on. Okay, so because the electron phonon coupling matrix is a huge dimension, so I can't show the elements here, but I can show you the basic data. For example, we start from the very beginning. The lattice constant is 10.5, and the lattice vectors, the symmetry operators, all this data can be used for your own demands. Yeah. So any questions? Okay.
Shiyu, I just have a very small comment. Actually, yeah, so H5LS might be not the best way to visualize data, but still, you know, if you do H5LS -D, then you can access the data. I mean, again, your Python script will be, of course, better to post-process it, but if you do H5LS -D, you can access the the values.
H5 HD.
H5, no, sorry, that's the same command, H5LS. Yes, and then a space and yeah, -D, and then like yeah, you can, for example, access the a lot parameter like that.
Thank you for letting me know this. Wow. Well, this command shows the element. I mean, in the data structure.
Yeah, basic data, maybe basic data, and a lot, something like that.
Okay, so yeah.
Yeah, and here we have all of it, and we can do like a lot, for example.
Yeah, yeah.
But HDF5 or your scripts are better ways to do that. Yeah, thanks.
Yeah, if you just want to say it, so it's a very convenient. Yeah, if you want to, I mean, to processing the data, you need to use the script, maybe better. Okay. So now you have know how to generate the EPR file and know what's in the EPR file. So let's move to the next task. Based on the EPR file, we would like to show you some very basic calculations. It's actually a preheating for the following hands-on session 3 and 4. Okay. The three calculations here is all is the interpolation step. First, we start from the bands. Okay, so first thing is to make a soft link to the APR file, because sometimes it's very huge. And then we need to run the Perturbo. Wow, very quick. You can see there are a YAML file. Actually, for the current release, we integrate many useful information in the YAML file. So you can post-processing the data from the YAML file. Here we use the.
Sorry, could you also keep the terminal window? I mean, yeah, when you return back, yeah, because we didn't.
Ah, okay, okay. Sorry. So we need a chair and you again. So okay, so we our group members, Shannon and Sergey and Ivan, prepared a very elegant post-processing package named Perturbo-Pi. So it's very easy to use. You see, just several lines we can perform the band plotting. Okay, so what we just need here now is just to execute the Python script. Oh, so it's Python 3. Okay, you can find there is an file named gallium arsenide band PNG, and then you can change it to your local OS. Go to the folder. Right. If you are a Mac, you can just open the. Let's copy. It's easy. Okay, just open. You can see the band. Any question? Or just need some time to figure it out? Okay, it's very easy. Next, please go to the next folder. We need to interpolate the phonon dispersion. We need to make a soft link to the EPR file and then to run the Perturbo. Sorry, we need to change the Docker.
In this file, there's also this gallium arsenide for band kpoints.kpt, right? So if I change it there, then is it?
You mean the band?
Yeah, exactly.
Okay.
Yeah, I'm still with. Yeah, I just looked at the picture, and so this is nice.
This file?
Yeah, exactly. So if I change it here,
yeah,
it's possible to change here, and then this will change the figure, right?
Yeah. Just the path.
Point.
Yeah.
Okay. Yeah.
Thank you for your question.
Yeah.
Okay. Let's go to the phonon dispersion folder. Okay, so.
A quick question. You have joined the electronic bands also in Perturbo, but how is it going to be different from the quantum espresso bands, or it will be the same?
Actually, it should be the same. The workflow is from the quantum expression. You have the ground state, right? And then we interpolated use the linear functions in the real space, and then we come to Perturbo to interpolate the band. Actually, it's the same. The physics is the same. Yeah.
So it's just using the interpolated version.
Yeah.
It's not anything.
You actually a quick comment. Could you go back to the bands folder?
Okay. Band folder.
Could you just like show them the format of the YAML file just so that they know that like this is where they can see the results?
Yeah, it's a good idea. YAML file. There are many important the input parameters because we do some unit conversion. So there is a two block before conversion and after conversion. You can see it based on your own need. And the basic data is always here. Yeah. So it's very many useful information. Here is the bands. If you need to draw the bands, you just need to read the information here. Actually, the YAML file can be treated as a dictionary data type based on the Python libraries. It's very easy to do some post processing. Then we go to the phonon version. We run it again. Okay. Yeah, it's finished. we can see the phonome dispersion YAML file again. This is not changed. Maybe some parameters. Most are not changed. We can go quick. I guess the symmetry operator may be useful for some guys. And this is the phonome dispersion. Number of modes is 6. Maybe we can go to the bottom. In the bottom, it shows the timing information. Okay. So we have the output, the YAML file output. We can perform the plotting. Just execute the script. Sorry. Okay. We have the PNG file once again. Change it to your local OS. Just open. Okay. I think it should be the same with the markdown file.
What happens there at the gamma point for
Sorry.
this optical highest branch? Is it
Welcome comments from our group members. Yeah,
at the gamma point? The highest band at the gamma point is seems like
Can you zoom into it?
this one.
Yeah,
Good discontinue.
this issue is because there are analytical contribution from the dynamic ranges of the dipole terms. So it should be. So this is called LOTO limiting. So this in the code, so Q equals 0 exactly, you cannot run that. So it's not real defined value. So there here. So in the practice, you may use a Q one close to 0, but it's not 0. If you just use 0, you will see this.
okay, good question.
Yeah, and then it goes
Yeah,
down.
and there was
Any question? Always the questions make the hands-on session interesting. Just run something is very boring. So let's move back and change it to our local OS. And then the last thing is the electron phonome matrix, the string. Here we want to make summation over the band to show you the strings on the phonome dispersion. Okay, so go to the first thing is to make a softening. Okay. So the calculation mode has been changed to electron phonome matrix. You should, because the electron phonome matrix has the index of the band and the Q point of the K point and Q point, so you should provide two K point list. Because we need to make the summation over the band index, you should to indicate the band window, and then to execute the perturbo. Wow, very quick. Same with the previous two tasks. What you need to do is just to run the Python script. Before that, maybe we can see the script. It's also very easy. I guess there is an object of the electron phonome matrix, and it has a method from YAML file and the post processing, and run it. We can ignore the warnings. I don't think it will affect our results. Okay, you have also a PNG file. Change it to your local OS.
So at gamma point, that's where you get negative value, so it does not fall.
Yeah, it's like 0 there. So just
Well, you mean here, right?
Yeah.
Yeah.
yeah, because it's a log.
Yeah, because the difference between the maximum value and the minimum value is very huge, so we change it to the log. Yeah.
So, I have a quick question. Previously in your talks, you have also shown a diagram about the magnitude of electron phonon coupling matrix, and it does not look like the phonon dispersion. Here you just use the color code to show the matrix.
Oh, it's just a different way of presenting the results. Yeah.
And in that plot, what's different there?
On this plot, we're plotting the phonon dispersion and overlaying it with the electron phonon matrix elements. On the other plot, the y-axis was the magnitude. Yeah.
Yeah, here
Here, the y-axis is like phonon energy.
yeah, we make the summation over there. I think the bands.
Make summation over bands. Okay, so make all the summation at every point you show the magnitude.
Yes, and we sum over all the
Then why do you have like, I also see some bands in that plot. Why do you have different branches?
Bands. Which plot do
The
in this file or
in the talk.
in the tutorial by Yao?
Yeah, maybe.
So Yao, please provide some insight.
Oh, I mean, like you have another plot which shows the matrix.
It's for silicon.
Yeah, for silicon, but why does it look different from the phonon dispersion?
I think
This is Scotty answer.
No, but it's because here she's saying we're plotting the phonon dispersion with the electron phonon matrix elements overlaid as a color, but your plot point was different. It was like this. Right? Is that what you're asking about?
Yeah,
I think the format. I mean the structure of the electron.
I don't think she's talking about what you showed in your tutorial. I think she's talking about like in a lecture we showed gallium arsenide, like the matrix elements on the y-axis. Not.
Oh, it's different plot. This is color.
Yeah, this is
I
green.
mean, in that plot, what branches is that? So in that
Are
plot,
those the bands also?
those are not bands.
Yeah,
Those
they're
are
not bad. Yeah, just electron phonon matrix element.
Then what's hard? Why does one horizontal point correspond to multiple values? In that plot.
Yeah, it creates to the band, but it's not that energy. It's like each phonon mode. How strong it is coupled to the electron. That's the value in the y-axis.
So in principle, you plot the color as a function of the K point.
Q point.
So you take the Q point.
Yeah.
So you take the lowest band and you look what for each Q point you look.
Yeah, you can use the color value to show.
Okay.
Yeah, it's like basically the color is now on the y-axis.
Yeah, because actually the electron phonon has many
Okay.
index,
So
band
you don't
index.
sum over these
Yeah.
bands, you still
Oh, sorry, these are the phonon modes. When you said bands, I
Oh,
thought you were talking
you
about the
don't sum
electron.
over those branches.
Yeah.
Yeah. Also from this file, you can also plot the phonon. Yeah, phonon dispersion. So something with this one, I will show you again. Can just check it. Open. It's actually the same. This is a phonon band. Yeah, just draw it again. No, nothing new. Okay. So that's all for the hands-on session 2. Any question?